Yeah, I was gonna say I don't really care. If you want to, you can try, but like the lowest of my priorities right now. Or I'm the kind of person that normally would try to do that. This semester, I mean, honestly, exactly. I never tried to use that word. There is assignments where have been kind of difficult. But honestly, compared to this and machine learning, it's a short yeah, if there is space for it. If there is, so say there were a source of values, you could potentially have 8 squares. So each one square has 8 squares around it. So yeah, so the size and one thing we noticed is that it's taking a while to get diagonal movement and lateral are identical. So like, so basically like moving so like moving 2 squares to the left and moving 2 squares diagonally. So it's not what do you call it? Yeah, we don't have it's not your standard. It's just what happened to measure from like to measure this like this. Measure from this point to this point. Who was in charge last week? Sorry? Who was in charge last week? Michael or Wyman? I think Michael. The hypothesis is, I mean, the distance is the greater of either x or y. It's weird. It takes a while to get used to, but once you do, it's called, I think it's called Chebyshev distance or something. Yes, but while it's just on the ground, it looks like it might be some sort of rating. So if you choose a criterion, it's determined by the number of carrying parts that it has. Each carrying part will be the carrying capacity and fit those. There's 50 energy on the ground and you have enough carrying capacity. Yeah, part of the thing is I believe you get but yeah, transferring it between carrying it just sounds like so and like if you're so because you can do math to figure out all this stuff, but an energy source with a pure multiplication has further 3 times the energy. And that is what you have, and it regenerates as soon as you harvest from it. For work part comes out. If you have 5 work parts, it was very the last thing from it will also regenerate. So 5 work parts. Exactly as it regenerates, but there will be gases. So, like if you're just going for that, I would go for like 6 work parts. I don't know where to This, I mean, this won't help you at all with anything like stock or like manipulation or whatever. I mean, you can just start the game and start the game.
Alright, let's start. So today we'll be talking about basically another powerful use of randomization, which is probably many of you have seen it in some form or the other. So this is generally the notion of sampling. Okay, so this is something everyone does all the time. So it's good to see how you reason about sampling algorithms. So before we start, let's recap what we did last time. Okay, so last time we looked at random hashing, okay, and we framed it as this problem of throwing. Oh, yeah.
Well, so the live stream wasn't up.
Yeah, so he's trying to figure out. Yeah, what was it?
But will the lecture be posted?
Last one or
Yeah,
the
because it
ones
wasn't
before?
live streaming, but will it still be posted?
It wasn't?
No.
It was a live stream?
No. And I even commented and no one commented that.
Okay. So there have been issues related to the video. So I think multiple people have emailed about this. So
No, that's different actually.
yeah, this is different. This is about the live stream.
Yeah.
So hopefully it will be uploaded, but
It is uploaded. You can see it right now, right?
Watch it now.
I guess so, because I can see it right now.
Okay.
there are also some numbering issues apparently. So we'll try to fix them.
The last two lectures, before the last one actually, they were not uploaded, but the last one is up.
Okay.
Yeah.
Thank you.
And we don't know the reason why the other two were not uploaded. Right?
Yeah. I guess Michael has them, but he hasn't uploaded them yet.
Hopefully we didn't lose them. Okay, let's see. Alright, so last time we spoke about hashing, and we viewed it as this process of, the simplest way to view it is as throwing some m balls into a collection of n bins. Okay? So you have n different bins and you have m balls, and you throw each one independently at random into one of these bins. Okay, so this was the process we were looking at last time. Okay? And so we tried to analyze various quantities here. Right? So the first question we asked was, will there be collisions? In the sense, will there be two different balls that hashed the same bin? Okay? And the answer we saw there was that this is extremely likely to happen. And even if m is much smaller than n, the number of balls you have is way smaller than n, it's only something like square root n, at least one collision is pretty likely to happen. Okay? So this is something we saw last time. Okay. And so this was what is called the birthday paradox. We also then focused on this case of m equals n. Okay, so in this case, you have exactly n balls that you are throwing into n different bins. And here, so the question was, if you have n balls and you throw them into n bins, you could ask, how evenly spread are these balls in these bins? Okay. So in expectation, the size of every bin is 1. Right? So if you fix a given bin and you ask, what's the expected number of balls that fall into this, then it's exactly equal to 1. Okay. So this is something we saw. But things don't always behave according to expectation. Okay. So this is the theme of, in general, of these kind of randomized algorithms. Okay, so you first figure out what it should be in expectation, then you figure out how much it could deviate from expectation. Okay, so in this case, we saw that there are roughly n over e empty bins. Okay, so e is 2.7. Okay, so it's roughly 2.7. So there are roughly n over e empty bins. Okay, so this is what we saw. And we also saw that there are bins with a lot of elements. So for instance, for any constant, like if I ask how many bins have 10 different elements, this is what we saw last time, there are a constant fraction of bins that have 10 different elements, that have capacity 10 or have 10 balls in them. So this is again what we saw, and then we said that the max bin size is roughly log n divided by log n. So I won't go into that, but in general our argument was the following. So we saw this powerful notion called linearity of expectation, okay? And we basically used this multiple times to deduce all these problems. Okay? So what we said was, suppose, let's take one of these examples. Okay, so let's take the empty bins. Okay. So we said we defined xi to be the random variable. It's a 0, 1 random variable, and it's 1 if bin I is empty. Okay. And then we said that the number of empty bins, you could write it as sum over I equals 1 through n of xi. Then we said that the expected value of this quantity is equal to the sum of the expected values of xi, and this number was fairly easy to compute. Okay, so this is, each xi is a 0, 1 random variable, so you compute the probability that it's equal to 1. Okay, so this is just equal to sum over I from 1 through n, probability that xi equals 1. And this in our setting turned out to be 1 over e. Okay, so this was 1 by e times n. Okay, for every I, this was equal to 1 by e. Therefore, you got this n by e. Okay. And then we did a similar kind of analysis for all the other questions that we saw. Okay. So this was in some sense what we did last time, a summary of what we did last time. Okay. So any questions about this? So this notion of linearity of expectations, as I said, is a very powerful one, and this splitting up of expectation of a sum into sum of expectations is true no matter how correlated these variables are. Okay. And that is the important point. Okay, so in this case, our xi's are somewhat correlated. They're not that correlated, but they're somewhat correlated, because if one bin is empty, then it's more likely that another bin is not empty. Okay. Because n balls have to go into all of these things. Right? So what linearity of expectation holds here in general. So actually before we go there, so how comfortable are you guys with this notion of independence of two random variables? Like are all of you familiar with this notion of, when do you say two random variables are independent of each other? I mean, intuitively I guess all of you have some sense, right? But like two coin tosses are by definition you would think are independent of each other, right? But then if you measure some property of coin toss and some other property, then maybe they're not independent. Okay? So I mean, so how many of you have at least seen the definition of independence at some point? Maybe you don't recollect it. Okay, so all of you have seen it at some point. So I would encourage you to go back and look at these things. Okay, so maybe I'll put up a link to some probability basics kind of thing. So for today, let's work with this basic assumption that if you have just two random variables, then independence means probability of x being something, given x being some small x, given y is some small y. So this is independent of small y. Okay? So this is equal to probability of capital X being small. Okay? So this is one working definition you could say of independence. Okay? But this holds only for two variables. Okay? So if you have a collection, then formally you have to say fix any subset of them, and the probability that some other variable takes on a particular value is independent of this fixing. So this is how you define independence for a collection of random variables. So this is good to keep in mind. So intuitively independent, you just think of them as independent coin tosses. Okay? So the outcome of one does not affect the outcome of other. Okay, so if you measure one, you don't affect the. Okay, so given that, so today the main kind of question we'll try to look at is sampling. Okay, so suppose you have two choices, donkey or elephant, and you want to pick one of them. Okay, so people pick one of them, let's say, and you want to estimate what is the likelihood that a person picks a donkey, okay, or something like this. Okay, so let's replace this by 1 or 0. So we have you have a population, okay, and so you can think of it as n different bits that you have. Okay, so P1, P2 to Pn. Each one is either a 0 or a 1. And let's say you want to figure out what is the fraction of these b's that are equal to 1. Okay, so question is, what's the fraction of 1s? So suppose this fraction, I call it p. Okay, so p is the fraction of 1s in this array. Now, if I pick a random sample from this array, what's the probability that you find a 1? Now, I said there are p fraction of 1s, right? So think of p as being, I don't know, a fourth or something. Right, so this array looks basically like 1/4 of them are 1s and the rest are 0s. Okay, so this is probably how the array looks like. And I'm asking, suppose I pick a random index, what's the probability that I see a 1? Yeah, it's, by definition it's exactly p, right? So this is a fact which we use when we try to estimate or predict elections and things like this, right? So you say, I'm going to sample a bunch of things. Okay? So I'm going to sample a bunch of random indices, okay? And I'm going to check what fraction of the sample is equal to 1. And that gives a good estimate for for the fraction of things that are 1 in the full array. So the question we want to understand is, how many do you sample? Okay, so how many independent samples do you take? And secondly, suppose you take a given number of samples, what guarantee do you get on the accuracy of the solution you find? Okay, so is this question clear? So we want to see, the question is, how accurate is the solution you get from k samples? So is it clear what we are doing with the k samples? You pick k indices at random with replacement. If k is bigger than square root n or something, then you can actually show that you will sample something twice. Okay? But that's fine. That's the right way to do it. And now you see what fraction of elements are 1 in that sample, and then you conclude that that is the p that you're doing. And we want to give some bounds on how good, how likely, how correct we are. So
we're trying to estimate p.
Yes. So this is the simplest setting where you're trying to estimate p. By the way, does this seem too bright for you guys too, or just me? Is it okay? You can all see clearly? Okay. All right. Okay, so let's start by studying this question. Okay, so an important notion when it comes to studying questions like this is this notion of variance. Okay, so So what we are getting at is we have an estimator. Okay, so we have some estimator, which let's call it x. Okay, so x is it's a random variable, and it's our estimator for p. And this is just the number of ones that you have in the sample that you obtain. So for any random variable, we've seen what the expected value is, right? So we've defined the notion of an expected value. So you could also ask, what is the variance of a random variable? Okay, so what is the variance? So before that, let's see a picture. Okay, so how does a typical random variable look like, right? So you have, it takes a real valued number. Okay, so this is the real line, and it maybe takes certain value with some probability, it takes some other value with some other probability, so on. Okay, so the height represents the probability that it takes this particular value. So I'm just drawing a discrete random variable. Okay. So the height could be the probability that it takes this value. This is the probability that it takes this particular value, and so on. Okay. So the expectation of x, we define this as integral over the whole real line. Integral over r, or this could be the range of x. Okay. If you have a discrete range, then it's just the sum over these things. Okay. Of x times the probability that capital X equals small x dx. Okay. If it's discrete, it's just a summation. This is how we define the expectation. Now, if you have a random variable like this, then presumably the expected value will be something over here. Okay, so let's say. So, but note that. So what's the broad question we are interested in, right? So we are interested in this question of how close random variables are to their expectation. Okay, so that's the question that we want to answer, right? Because if you look at this sampling example, so if you pick the random element, the expected value is exactly p. Okay, so the expected value is p, and we are asking the question, how close is our estimator to p? Okay. So what we are generally interested in is this notion of how close we are, how close a random variable is to its expectation. Okay. So one thing you could ask is, okay, so what's the expected value of this, so suppose you call this mu whole square. So in this example, so this is the expected value of this random variable, but note that the variable never actually takes the value mu. Okay, so mu is here. It's always a little bit off from mu, right? So sometimes it's here, sometimes it's here, sometimes it's here, and sometimes it's there. Okay, even though the expectation is actually in the middle. And this is often true for discrete variables, right? So if you have 1 happening with probability 1/4 and 0 happening with probability 3/4, your expectation is 1/4, but your random variable never actually takes the value 1/4. Okay, so this is the quantity we are interested in, right? So we are interested in how far it is. So one quantity that captures this sort of deviation is what's called it's called the variance. Okay, and the variance is defined to be the expected value of this. Okay, so in some sense, what you're measuring is it's the expected value of distances like this. So with some probability you are this distance from mu, with some other probability you are this distance from mu, and so on. So the variance is the expected value of the square distance to the mean. And this is a very useful parameter for a random variable, okay, as we will see. So this, you can also write this down as, if you really want, you could write it in the same kind of integral way. So you could say it's just an expected value of x minus mu squared times probability of x equals x. So this is just the definition of expectation. I'm using it on, think of x minus mu whole squared as itself a random variable. Then I'm just using the definition of expectation. Okay. So if you haven't done computations like this, you should, you should figure out how to compute the variance of standard random variables. Okay. So let's not get into that. So, how many of you have done variance computations for like simple enough random variables? Okay, good fraction. So I guess it's yeah. If you want, you should recap these things. Okay. All right. So this is an important concept. So, okay. So the next thing we are going to see to understand this question is, so suppose you have, is what's called the binomial distribution. This is again something that often shows up when you analyze these kind of probabilistic processes. Okay? So the question you ask here is, suppose you toss k coins, okay? And each coin has exactly a probability of half of turning up heads. Question you're asking is, how many heads do you see? And this graph shows exactly the probability. Okay, so this height is the probability that you see 3 heads. So it turns out something like 0.3. Probability that you see 2 heads is something like here, and so on. Okay, and this sort of bell curve is how such graphs look like. Okay, so if you have k coin tosses, each with probability half, then it looks like a symmetric bell curve like this. Okay, so I just wanted to draw this so that you understand how it looks like. So in our setting, so what are we doing, right? So we were sampling, we were essentially doing k coin tosses. Each coin toss succeeded with probability p. And then we were trying to count how many tosses came up heads, right? So that's what we were doing for this election prediction. So you can figure out how this looks like. So if you do n coin tosses, suppose you do n coin tosses, each heads with probability p. Okay. And now you see how many turned up heads. Okay, so this is the count of number of heads. So this number, if p equals half, then this is how it looks like. It looks like a symmetric curve. If p is, let me draw how it looks like for say p equals 1/4. Okay, so here it looks a little bit lopsided. So if I do n coin tosses, how many do I expect to be heads? So suppose I know p is 1/4. You expect 1/4, n over 4 of them to be heads, right? So you expect some kind of a peak at n over 4. And so the range is only 0 through n. Okay, so this is the range in which this is the number of heads that you could potentially see. And sure enough, the graph turns out to look something like this. So it will peak at 1/4 and then it will slowly drop off. Okay, and it will drop off exponentially. So the question we want to analyze, if you want to think of it pictorially, is what's the likelihood that you are far out from this expectation? Right? So if this is n by 4, what's the likelihood that you deviate by something like epsilon times n? Okay. So this number is epsilon times n. Okay. So is what we are doing clear? So you have so if you go back to the election example, so when you sample a random element, and if you see if inspect if it's 0 or 1, you get a 1 with probability p, you get a 0 otherwise. And here I'm saying how many heads do you get if you sample n different different people? And in expectation, you expect to see n times p. Okay? So your expectation is exactly n times p, and the question you're asking is, what's the probability that you deviate by more than epsilon n? Okay? So what's the probability that your estimate is off by epsilon? For instance, you could think of deviation as both positive deviation and negative deviation. Let's first look at the positive side. Okay, so what's the probability the number of heads is more than 1/4 plus epsilon times n? Okay. So how would you normally answer a question like this? So in this very simple scenario, so in fact, what if I just ask you, what is the probability that I see, actually let's take an extreme example. Okay. So I have a coin and I toss it n different times. Each time it has a probability p of coming up heads. What's the likelihood that you never see a heads? It's so let's see the simpler probability. So it's a probability that, let's give a name for this. Okay, so the count of number of heads, let's call it capital H. Okay, so capital H is a random variable. And what's the probability that capital H equals 0 is 1 minus p to the n. Right? Because you want it to be 0 all the time. And so also you have capital H, you have some probability for capital H equals n if you want. So this is p to the n. More generally, you can write a formula for what it should be for every k. Right? So, and this, it's exactly n choose k times p to the k times 1 minus p to n minus k. Okay, so that's why this is called the binomial distribution, by the way, because so this is just a binomial coefficient times the appropriate probability. Okay, so for those of you who recognize that. So, okay, so we know what's the probability for every k, right? So you can just compute this thing, and then you can just say it is sum over k bigger than or equal to n, k bigger than or equal to n times 1/4 plus epsilon of this quantity. Okay. So this is true, but it's also it's not very intuitive, right? So how big is this quantity? Like suppose I tell you epsilon is 0.1, then you don't have a very easy way to estimate this quantity, right? So is this going to be exponentially small in n, or what's it going to be, right? So suppose p is 1/4 and epsilon is 0.1. Okay, what do you expect this summation to be? So some of you may be able to guess, but it's still messy, right? You don't want to deal with stuff like this. You want a nicer way of analyzing these kind of quantities. So this is what we'll figure out how to do today. Okay, so and we want to understand something that will work more generally, okay, not just in the simple setting of coin tosses. All right. So these are what are called large deviation bombs. Okay, so the kind of questions we'll ask is: you have a random variable. X, and we want to study what's the probability that X deviates from its expectation, okay, from the expected value of x by some quantity lambda. Okay, so this is what is called a large deviation bound. Okay, so, and this is intuitively why it arises. Okay, so you sample something and you want to know how good that estimator is. Okay, so this is usually the context in which such a question arises. Okay. So first, let's see if something we already know says something. Okay, so I already said the variance of a random variable. So I said variance of x. It's supposed to measure roughly this, right? So the variance is supposed to measure the expected value of this difference. Okay, so it's like this. It's x minus e of x whole square. So let's take an example. So suppose I have a random variable in which the variance is suppose I tell you the variance is 1, okay, which means the expected value of this square deviation is equal to 1. And now I ask you, what is the probability that x minus ex is bigger than 100? Okay, so how would you answer this? So I claim you already know the answer to this. So is the question clear? You have a random variable, it takes real values and its expectation is mu. What I am saying is the variance is 1, okay, which means that in expectation its square distance from mu is 1. Okay. Now, what's the likelihood that this is more than 100? That you are like 100 away from this? Any guesses? So how would you do this? You can try to use Markov's inequality, right? Because what Markov's inequality tells you is, if you have a random variable which is always non-negative, okay, so in this case, suppose I think of this as my random variable. Okay, so the expected value, the x minus ex squared. Okay. So this is a new random variable, I can call it y, right? All I'm asking is, when is y bigger than 100 squared, right? So if this is equal to 100, then x minus e of x squared is 100 squared. So I'm asking, what's the likelihood that y is more than 10,000? So the probability of this event is exactly equal to the probability of y being more than 10,000. Now y is some random variable whose expectation is 1, and that's what I just told you. Okay, because let me write this down formally. Okay, so this is what's called Chebyshev's inequality, by the way. Okay. So what it says is, so variance is defined as the expected value of x minus, let me write mu for the expectation so that you don't get confused with x minus ex and so on. Expectations inside expectations and so on. Okay. So mu is the expected value. So the variance is this, and this you can think of it as expected value of y, where y is a non-negative random variable. I'm just defining y to be x minus mu whole square. So y is a perfectly legitimate random variable, right? So it's just defined in terms of x. And the expected value of y is this variance. Now all we are asking is, what is the probability that x minus mu is bigger than lambda, okay, for some lambda. And this is exactly equivalent to the probability that y is bigger than lambda squared, right? Because absolute value of x minus mu is bigger than lambda is equivalent to saying x minus mu whole squared is bigger than lambda squared. Okay, so that's what this is. And this you can now use Markov to conclude that this is smaller than or equal to the expected value of y divided by lambda squared. Okay, so Markov basically said if you have a non-negative random variable, the probability that you are t times away from its expectation is 1 by t. Okay, so you can think of this as here the t as being lambda squared by e of y times e of y. Okay. So this is just this, and now you put it into the form where you know I mean this is the form of Markov inequality that you knew, right? So this is t, and this is 1 over t. Okay. So is it clear how Markov's inequality implies this? It's actually very simple. So if you don't see it, also you can go back and verify. So this is a powerful inequality. It's called Chebyshev's inequality, and basically it tells you what's the likelihood that some random variable deviates from its expectation. Okay? So if you have a random variable whose variance is small, then the likelihood that it deviates from its expectation is also small. Okay? So that's the general use case for this. And this is variance divided by lambda squared. Okay. So just like we wrote, so let me also so let me also define. So I guess all of you must have seen this, but a standard deviation of a random variable is just defined to be the square root of its variance. Okay, so that's standard deviation. This is just an aside. I wanted to tell you why they call it standard deviation. Okay, so standard deviation is square root of variance. Okay, so variance was the expected value of the squared deviation, right? So it's the expected value of the squared deviation. So in some sense, typically the squared deviation is roughly square root of it's roughly the variance, right? So that's what it means by the expected value. And that's why this is called the standard deviation, because usually you expect this random variable to vary about this much, okay, about square root of variance. And what this Chebyshev's inequality tells you is that the likelihood that it deviates by much more than its standard deviation is small. Okay. So let's call this sigma. Okay. So that variance is sigma squared. Then another way to write Chebyshev's inequality is probability that x minus mu is bigger than some t times sigma is at most 1 by t squared. Okay. For me at least, this is more intuitive way of writing Chebyshev's inequality, because sigma is how much I expect it to deviate, okay. And what this is saying is the likelihood that it deviates by more than t times sigma is actually pretty small. Okay. So intuitively it makes more sense. right? So this again follows just by standard manipulations and plugging in the value of variance. So any questions about this? Okay. So this is a general statement which holds for any random variable whose variance can be bounded. But
Does it have to be a discrete random variable?
no, this is true in general. This is true for even continuous random variables because Markov is generally applicable.
What's that at t times what on the last line?
Sigma. So I'm defining sigma to be standard deviation, and so sigma squared is the variance. So I'm just introducing some notation. So that's the standard notation for variance. The people usually write the standard deviation as sigma, and this is what it is. So, how many of you have heard this word 6 sigma or 3 sigma, something like that? So usually when you measure the quality of something, you say that you don't vary too much from your variance should not be more than 6 times sigma. Okay? And what this says is that for any random variable, basically, the probability that it's more than 6 times sigma is like 1 over 36. So it implies something like that. Usually you expect it to be much smaller, so we'll see something like that. But this is generally true for any random variable. So next what we'll see is, so specifically for the kind of random variables we are interested in, so what in our case the x is it's actually a sum of independent variables, right? So if you recall, x is the number of heads we were counting. Okay? So you were counting a bunch. You were tossing a bunch of coins, and you were counting the number of times it turned out to be heads, right? So our x is actually a sum of independent coin tosses. Okay? So for such random variables, can you get better bounds? Okay, so that's the question we'd like to understand. So I'll show that in a bit. Okay, so formally the question you have is, you have x1, x2 to x n. So these are, let's say, independent. Think of it as coin tosses. So coin tosses are also called Bernoulli random variables. Okay, so it's each xi is 1 with probability pi, 0 otherwise. So in our setting, all the pi's are equal to p. Okay? But this is a slightly more general theorem that I'm going to write down. So here the point is you have xi as a reference, and then you are interested in this y, which is or let me call it x, which is sum over I equals 1 through n of xi. And these are independent coin tosses. Okay, so independence again means what I said. The question we want to understand is, what is the probability that x minus the expected value of x is more than some lambda. Okay. So here again we are interested in lambda being some multiple of the standard deviation. Okay, so that's the quantity of actual interest. Okay, so what is the variance of x? So what's the variance of x here? So x is actually the sum. So the definition is, it's the expected value of sum over I xi minus the expected value of sum over I xi, the whole thing squared. It looks very messy, right? But one exercise which, if you haven't done it, you should do it, is that if you have independent random variables,
It cancels out.
yeah, so it will turn out that variance of x is equal to the sum of the variances of xi. Okay, so this will turn out to be the sum over I variance of xi. Okay, so, and the reason this is true is because of something like what you said. Basically, you can split this as sum over x minus expected value of xi. So this you can use linearity of expectation. And then if you have xi, xj terms, the expected value will be 0. Okay, so this is a simple exercise. So if you've never seen it, this is fun to work out. Okay. So the variance of x will be equal to the sum of the variances. And each xi is a simple coin toss, right? So what is, yeah. So what's the variance of each coin toss? So this is, this we can try to evaluate, right? So it's the expectation over just this xi of xi minus pi whole square. Okay. So the variance of a coin toss. Let's so coin toss is a very simple random variable, right? So it's either 0 or 1. Okay. So you can compute it by basically saying with probability p, the variance is 1 minus p whole square, plus with probability 1 minus p, it will be p square. Okay. So I leave it to you guys to verify this. Okay, so this is actually easy to compute, yeah, and this will also tell you how to compute these variances, and this will be equal to pi times 1 minus pi. Okay. So this is the variance of one random variable. And so the sum of the variances is basically sum over I pi times 1 minus pi. So the variance of each coin toss is pi times 1 minus pi, and the sum of the variances is sum over I of this. So another fun fact for those of you who don't know is variance is additive like this only if these things are independent. Okay, so I said that the expected value of x, expected value of x is sum of the expected values. That's linearity of expectation. That's true no matter what. Okay, but the variance adds up only if these variables are independent. Okay. Okay, so you have so this is the variance of x. And the question we want is so we want to answer this. Okay. So you expect lambda to be roughly square root of this quantity. Okay. So usually you expect this x minus e of x to be square root of this quantity. So let's just define this as sigma squared. And what the previous theorem, what Chebyshev tells you is that the probability of this is smaller than or equal to lambda divided by sigma squared. Okay. So do you guys see this? So this is just, lambda squared divided by sigma squared. Right? So this is what Chebyshev tells you. Because I'm just asking, so you can plug it in and verify. Let me not, yeah.
Can you do the final step from how do you get from p
Oh, so that was the variance of one coin toss. Okay. So what I said was variance of x is sum over I variance of xi. Okay. Once you accept that, then I am computing what is the variance of xi. Okay. And that is that computation I did there. Okay. So for xi, the xi is just a 0, 1 random variable.
How do we get from there to P to 1 PI from?
Oh, so this, it's because of this. So pi times 1 minus pi squared plus this. So if you take pi times 1 minus pi out, then you just get p plus 1 minus p, which is 1. Okay. This is one of these standard things that goes on in. Yeah. So it turns out that the variance of one coin toss is pi times 1 minus pi. And once you accept that, then it's just sum of those, which is why you get sum of those. Yeah, it's a good point. Yeah, so these kind of calculations, it's one of these things that if you do them a couple of times, they become second nature. But if you haven't seen them, then it looks funny. Okay, so I would encourage you to just go do some of these calculations. But the main point here is not quite how to compute the variance. That's why I'm not spending too much time on this. The point is, what Chebyshev tells you is that if this variance, whatever it is, if you denote this by sigma squared, so then the probability that your deviation, the deviation from expectation is more than lambda, is at most lambda squared by sigma squared. So this is what Chebyshev tells us. And think of lambda as being, let's say, 100 sigma. Okay? So this tells you that this is, oh, I'm sorry, this should be the other way around. So this should be sigma squared by lambda squared. Yeah. So yeah, this is a typo. So if lambda, if you set it to 100 times sigma, this will evaluate to something like 1 by 10 to the 4. So it tells you that it's pretty unlikely. Okay? So it tells you that the probability that you are 100 away from you are 100 factor off from the standard deviation is 1 over 100 squared. So that's what Chebyshev tells us. But there's actually a much stronger bound in this sort of settings, which is called the Chernoff bound. Okay, so what it says is the probability is not just something like this, but it's actually exponentially small in this quantity. Okay, so that's what's called Chernoff bound. So let me show you the final bound, then we'll try to interpret it. Okay, so this is a slightly messy slide. So maybe I will. Okay. So I'll try to create a new slide and write it in a more interpretable form. Okay. So. So this is Chernoff bound. So this is actually a pretty general theorem, and what it says is if you have a sum of independent random variables, okay, so if x is a sum of independent random variables, okay, and its variance is the variance of the sum, okay, and as of now think of xi is 0, 1 random variable. Okay, so these are each Bernoulli random variables and they are independent. And suppose the variance is sigma squared, then the probability that x minus the expectation, variance is sigma squared, also suppose mu is expected value of x, is more than lambda is smaller than or equal to e to the minus lambda squared by 4 sigma squared. Okay. So this is a very powerful statement. Okay, so it's a much stronger bound than what Chebyshev's inequality tells us. Okay. So what it says is, for example, if to see the power of this, suppose you set lambda equals 10 sigma, okay, or yeah, let's say 20 sigma. Then what Chebyshev's inequality tells us is that this probability is smaller than or equal to something like 1 over 400. Well, this tells you something like it's smaller than or equal to e to the minus 100. Okay. So this is an extremely tiny quantity, right? So this is probably the inverse of the number of atoms in the universe, something like this, right? So this is an extremely tiny quantity, and here this is just 1 over 400. Okay? So this is the difference between the two. That Chebyshev's inequality, that Chernoff bound usually gives you a really strong inequality, but it's also less general. Okay, so it is this sort of inequality holds only if you have a sum of independent random variables. Okay, so any questions about this? I expect you to have some questions because this is actually a pretty deep theorem. And what it, right, so it basically says that the likelihood that you are even a small constant away from the standard deviation is actually very tiny. Okay. And this, another way to think about this is that this x behaves like a Gaussian of mean mu and variance roughly sigma squared. Okay, so that's another way of thinking about this thing. Okay. So its tails look like that. Alright. So we'll see some examples of this so you'll know how to apply this theorem. So even though this looks much more powerful than Chebyshev, turns out the kind of proof is very similar. Okay, so all these theorems are proved by taking some appropriate function. Like if you remember how we proved Chebyshev's inequality, we looked at this random variable y, which was x minus mu whole squared, and then use Markov on this, right? So it turns out if you look at y equals e to the some t times x minus mu, and you use Markov on this, you get Chernoff. Okay, so all these are actually kind of very nicely related to each other, but it's just that the bound that this gives is much stronger. And to analyze this quantity, you have to use the fact that x is the sum of independent random variables. Okay, so that's where we are using independence. Okay. So things you should remember are Chernoff bound is much stronger, but it's more limited. It's only useful when you have sum of independent random variables. Okay. So let me do this. Let's see an example. So again, we have this thing. You have this. You have a bit sequence b1, b2 up to bn. Each one is 0, 1, and I told you that if I picked some index at random, So it follows this, it's like a Bernoulli, and xi equals 1 with probability p, 0 otherwise. This is true for all I. Okay, so if I pick any random thing, it's 1 with probability p, 0 otherwise. And what we said is my estimate is 1 by n times sum, estimate for p is 1 would be sum over I xi. And what's the variance of this estimate? So we saw this before, right? So if you didn't have this 1 over n, I said that variance of a sum is equal to the sum of the variances. Okay. So if you didn't have this 1 by n, it would just have been sum over I variance of xi. And variance of xi I said is p times 1 minus p. Now if you had a 1 by n, everything scales by 1 by n, and so this becomes 1 by n squared. Okay, because you're looking at x minus e of x whole squared, right? So in the whole squared you have 1 by n squared. So this you can easily work out. And this turns out to be p times 1 minus p divided by n. So one of the n's, you have n different elements in the sum. One of the n, so that's why one of the n's cancels with n squared. Okay, so that's why you have this as the variance. So the thing to observe is that p is a constant and this drops off as 1 over n. So what this is telling you is that if you take n different samples, the variance is going down as 1 by n. Okay? So the standard deviation goes off as 1 by square root n. Right? And yeah. So let's think of p as 1/4, so that I think of this as roughly some constant, so it's like 1 by, let me just write it as 1 by 5n or something. Okay, so probably not correct, but it's close enough. Okay. So this is what I have, this is the variance. So now what does Chernoff bound tell us? Right? So it tells us that probability that, so this is the random variable x, which is our estimate. X minus the expectation is always p. So this is more than, let's say 10 times square root of 1 by 5n is less than or equal to e to the, if I just use the 20 as I did before, then I get e to the minus 100. Right? So what this is telling us is that the probability that this estimate differs from the true p by more than this amount is extremely tiny. Okay, so this is what Chernoff bound is telling us. And so suppose I pick n equals 10,000 or yeah, whatever it is, so that I make this I have to make this n small enough, I mean n large enough, then I can make this thing pretty small. Okay. So actually let's parameterize it, let's be a little bit more formal, and suppose I pick, I want this to evaluate to something like, so suppose I pick n to be equal to some c by epsilon squared, so let's think of it as 100 by epsilon squared. Then you can see that the probability that this differs by more than epsilon is actually extremely tiny. Okay. So you can do the calculation here. So if I set n to be 100 divided by epsilon squared, okay, so then you get that this probability, okay, so if I plug in n equals 100 by epsilon squared, then you get probability that x minus p is more than epsilon is less than e to the minus 100. Okay. So So all I have to take is some constant by epsilon squared many samples. Okay, and then I'll have an extremely high guarantee that I'm within an epsilon of this law. Okay. So this is why when people do polling, so if you often have to do something like if you want within an accuracy of epsilon, you have to do roughly 1 over epsilon squared. You have to poll roughly 1 over epsilon squared people. Okay. And this is the kind of guarantee that you get in that case.
But you also have to make sure that their votes are independent.
Yes, so that is often the bigger problem. Okay, so this is always understood, right? So this is easy to estimate. But if your polling is biased, then of course you get a bad answer. Okay, so most of the resources in polling go into making it uniform. Okay, so but if you can do uniform sampling, then everything is really well understood. So, all right. Yeah, so here you can play with these kind of bounds. You can say, what if I don't want such a good accuracy, then, such a good failure probability, then can I get away with less samples? Turns out you can, and so on. Okay, so this is all straightforward. So let's move on. Okay, so let me skip this. We'll come back to this in a second. So let's see another application of Chernoff bond, which I guess some of you might have also come across. So it's this notion of random walk on a line. Okay, so suppose I have a particle. Okay, so it starts off. So suppose I have a person or something, and there is the infinite line. And at every step, at every time step, you take one step to the right or one step to the left. Okay, and you do this at random. Okay, so you go right with probability half and left with probability half. And this is done independently. Okay, so at every step, you just make an independent decision whether to go right or left. Okay. So your sequence of steps could be right, left, left, whatever. Okay, so think of tossing a coin at every step and moving left or right. Okay. So this is often called a random walk, or sometimes people call it a drunkard's walk or something like this too. So, but historically, this kind of process, even though it looks like a very toy problem, so this arose in what's called the study of Brownian motion. Okay. So it's about how particles in a fluid, when they collide with each other, they approximately move like this. Okay, so you can, they move in clearly a deterministic fashion, but you can model it as a randomized thing. Okay, so that's the cool thing in. So it's one of these early papers of Einstein which modeled particle motion as Brownian motion. Okay. Anyway, so these kind of things show up all the time. So that's what I want to say. And but the setting is very simple. Okay, so you have at every step you move left or right. And so what are we interested in? Okay, so this process happens for a while. Okay, so you move around, and let's say you move for n steps. Okay, say we move for n steps. Okay. So the question is, how far away from the origin would you be? Okay, so after you move forward, you move backward, and so on, and then the question is, how far away are you? Right. So if your expected position is, let's call it x after n steps, then what is the absolute value of x? Let's call it x superscript n. So just do. So how would you analyze this? So given what we've seen so far.
Randomly, if you move right, it's 1. If you move left, it's -1.
Yeah, so this is a positional random variable, so it makes sense to write this as, you can write you can write x superscript n as a sum of independent random variables, right? So every time you move right or left. And this you can write it as, let's call this y1 plus y2 to yn. Each one is an independent random variable, it's plus or minus 1. So this is very similar to what we had before. So earlier we had 0, 1 variables, now we have minus 1, 1 variables. But it's the same notion, right? So you still either move left or right. So this is how you can write this. And once you have this, now you can do all kinds of things, right? So what is expected value of xn? It's 0 because each yi has expectation 0, and each yi is plus 1 with probability half, minus 1 with probability half. So this is 0. And what we are asking here is something like, what is expected value of absolute value of xn? But for that we know how to analyze it. You would just say, what is xn squared? Okay, so, and this is exactly the variance of xn, because expected value of xn is 0. So you can write this as e of xn minus expected value mu which is 0 squared. Okay. This is the sum of the variances. Okay. And there are n terms. Each one you can compute the variance. It will turn out to be, I think, 1. Okay. So this is exactly n. So yeah, that's because e of yi is 1. So this will be n. So typically you expect it to be something like square root n away. Okay, so that's what this thing tells you. Okay. And you can also see that you can now immediately apply Chernoff bound, and then you can say the probability that xn is more than, let's say, some c times root n. So less than equal to e to the minus c squared by 3. Okay, but maybe I wrote by 4. Sorry. So is this clear? So this is what we said was would follow from Chernoff bounds, right? So the probability that so probability that your lambda away is lambda squared divided by 4 sigma squared. And if you think of lambda as being a multiple of sigma, then I'm saying lambda is like c sigma. So you get e to the minus c squared by 4. So this is an easy application. I was hoping to... Yeah, so let's do this application also, because we saw balls and bins last time while it's still fresh. So let's look at this other simple setting. So suppose now you have m balls and n bins, and think of m as being a multiple of n. Okay, so think of m as being c times n. So c, if you want, think of it as some constant, okay, 100 or something. So what are we asking? So the question is, firstly, what is the expected size of each bit? So what's the expected size of each bit? It's actually c, because you have more. You have c times n balls.
Okay.
Yeah. So this is c. Okay. So the expected. So you can again, let's say I define xi equals size of bin I. Then expected value of xi equals C. The question I want to answer is, what is the probability that xi minus c is more than some lambda, right? So how much does this deviate from the c? So this is the question we want to answer. And I claim that you can solve this kind of a problem also using Chernoff bound. So how would you write xi as a sum of random variables? Any ideas? So what's the definition of xi, right? Xi is the count of how many balls ended up in bin I. Okay. So essentially, yeah.
So it's a 1-0 thing where P is 1 over the number of bins.
Yeah, exactly, right? So you can think of xi as sum over all the balls, the indicator of whether the ball fell into bin I, right? So it's sum over balls j. You can define a random variable which I'll call yji. So this is 1 if ball j was placed in bin I. And 0 otherwise. So now you wrote each xi, you can write it as this, and now this is just a 0-1 random variable, and you can just use your favorite Chernoff and deviation bound. Okay. So this is how you analyze these kind of load balancing type questions. Okay, so this is like a load balancing question, right? Now I'm asking. So this is the expected number of balls that I expect to fall into this bin, and I'm asking what's the likelihood that it deviates by lambda. And you can analyze this also using Chernoff. Okay, so in this case you can probably do direct calculation. Direct calculation is messy. So this is a clean way of doing it. So one thing which is a non-application is what's the likelihood that n by 2 bins are empty? Okay, so you could say, oh, I have some random variable xi which is 1 if bin I is empty and 0 otherwise. Okay. And now I'm just asking what's the probability that sum over ixi is more than n by 2. So you might be very tempted to use Chernoff bounds, right? It's easy to get carried away at this point because each xi you know its expectation and it's 1 by e. So you can say, okay, what's the probability that this minus n by e is more than something? Then you could try to use Chernoff bounds, okay? But this doesn't work. Any reason why? Sorry? Yeah, exactly. So basically these are not independent events. Okay, so xi and xj are random variables, xi is not independent of xj. The reason is what he said, that if a bunch of bins are empty, then the likelihood that some other bin is empty is actually smaller than what it would have been to start with. All the balls have to go somewhere. So yeah, so you should be careful when doing Chernoff bound. Should be careful about independence. Okay, so that's what I wanted to illustrate. Okay, so next time we can start afresh with